So we're going to talk about torque, and then we're going to talk about levers. So let's start with torque. So what torque is it's a rotational force, right? And it's measured in units called the Newton meter. That's Newton meter. And the symbol for that is N.M. And 1 Newton meter is the amount of force, or the amount of torque that you get if you are trying to twist something using 1 Newton of force. So there's 1 Newton being applied there, and you're trying to twist something over here. Now, if that's 1 Newton and this distance is 1 meter, then this is 1 Newton meter of torque. And what happens, and I think this should be reasonably intuitive, right, is that if you're trying to put torque on something, let's say you're trying to tighten up a bolt, well, the longer your moment arm is, and that's a term that we use quite a bit, let's say this moment arm is 2 meters, and you're still putting 1 Newton in there, well, you're going to have more torque at this point here. Right, you're going to be able to put more twisting force on that point. And that is, well, it's not because, but that leads us really nicely to this little formula, which is torque, and we use the Greek letter tau for torque. Torque is equal to force multiplied by distance. And so if you want to know how much torque you're applying by putting sort of a force on something using some sort of arm or lever of some sort, that is the formula that you are going to use. And so let's do a real quick question. And let's use this spanner, seeing as it's just sitting here. Let's say that this spanner is 30 centimeters long. And let's say you're a stout human. You're capable of putting in, let's say, 600 newtons of force. You're giving it the beans. And so you want to know, okay, how much torque am I going to put on this nut? So we use our formula, torque equals force multiplied by distance. Now, we're measuring torque in Newton meters, so our distance needs to be in meters. So we know that our distance is equal to 30 centimeters, and that is 0.3 meters. Our force is already in newtons, so that's fine. So we can just plug in our values. So 600 newtons multiplied by 0.3 meters is going to give us bit of calculator because my mental arithmetic is poor. That's going to give us 180 Newton meters, which is quite a bit of torque. One thing that I'll say really quickly is that nuts and bolts and things that are threaded, we actually measure the tightness of those things in, well, we measure it in Newton meters because we use SI units, but you can use things like foot pounds. They're all of these units of force multiplied by distance. And so we use the Newton meter because those are the units that we use. And so I hope you can see that if we double the length of this lever, well, if we were to make this lever 0.6, then we would be multiplying 600 by 0.6. And so we would be achieving 360 Newton meters of torque. If we halve the lever, well, then we'd be multiplying this by 0.15. And so we'd be applying 90 Newton meters of torque. Right, so this is how we figure out Newton meters. Now, real quick, occasionally you'll see a question and it'll be like, here's a situation where you're applying some torque or you're using torque to apply some sort of force, and it'll give you this as your distance. Remembering that when we take our distance, we're measuring from the axis of rotation out to where the force is being applied. So in those situations, it would be the radius. Just something to keep in mind. Now, looking at this, I've put an electric motor down here because when we have motors and things with shafts and various things that spin, we need a way to measure how much force they're able to achieve. And so we use the Newton meter for that. So let's say, for example, that this electric motor is rated for something like, let's just say it's 400 Newton meters. Now that might be unrealistically low, given that this looks like a pretty big motor, but it's just argument's sake. So 400 Newton meters. And to this, we have attached, some sort of big wheel. And we want to know, okay, using this wheel at the outside of this wheel, what is the force that we're able to apply using that wheel? And so let's say it's a big wheel. It is 800 millimeters. And so we need to know, okay, so we've got a formula. Torque equals force multiplied by distance. We need to figure out force. So we need to get force on its own. And so what we need to do is we need to divide both sides of our equation by distance. And then we can cancel out our like terms. And we can rewrite this as force is equal to torque over distance. Now, distance here is going to be measured from the center of rotation. So that would be the shaft of our motor. And that's going to be half of our diameter. So this would be 400 millimeters. So distance equals 400. And so that in meters, again, because we need it in meters, is 0.4 meters. And so we can plug those into our formula. So we've got 400 Newton meters, and that's going to be multiplied, or divided by 0.4 meters. And we are going to end up with, oh wait, I can figure that out in my head. We are going to end up with 100 newtons. And hopefully you can see if we, no it's not, you spud. Ugh, 1,000 newtons. It would be good if I could math right. Right, so hopefully what you can see from this is that the larger this distance here, if we're using torque to generate a force at a distance, the larger this distance, right, the less force we're able to apply. And the smaller this distance, the greater force we're able to apply. Because as this number, this distance here gets larger and larger, it is going to produce a smaller and smaller output force. Cool, so how does this apply to levers? Well, we've got these two kids sitting on this swing. Let me write down levers for you. So this is a lever. A wheelbarrow is also a lever, and we'll talk about different classes of lever in just a second. But let's look at this. If we think about what's going on here, we've got this little girl, and she is applying a force, and this little boy, and he's applying a force. We've also got an axis that they're both rotating around or oscillating around more correctly. And we've got a distance from that axis. And when we're talking about levers, we call this a fulcrum, right? And we use a lowercase f for fulcrum. Now, if we look at what's going on here, we've got a force, we've got a distance, and we've got a spot that we're spinning around. We've got all the exact same stuff that we had when we were talking about torque. And over here with this boy, we've got a force, we've got another distance, and we've got an axis that we're rotating around. So we've got another torque over here. So lever problems are really two torque problems, or a problem involving two torques. And when we're working out lever problems, we figure out, okay, so what would it take to balance this lever system? You know, what would it take so that this little boy and this little girl were sitting in equilibrium? Because if we can figure out, okay, if we've got them in equilibrium where they're balanced perfectly, then we can do some work with those levers, right? Because one of the things we want to move with the lever might be super heavy, like the scenario where you've got a rock and you're trying to move that rock, and you are but a small and squishy person. All right, that's a big rock. So if we've got those balanced, then we've got one torque over here and one torque over here. So let's write out one torque. So torque equals force multiplied by distance. So that's this torque over here. And we've got another torque over here. Torque equals force multiplied by distance. And if they're in equilibrium, well, then the torques have to be the same, right? If it's perfectly balanced, then the torques have to be the same. And so we can rewrite the equation where one torque equals the other torque. And if one torque equals the other torque, then one force multiplied by distance and the other force multiplied by distance also have to be equal. So you can rewrite this equation as force multiplied by distance is equal to force multiplied by distance. And when we're looking at lever problems, we say that we have an input force, an output force, and therefore we also have an input distance and an output distance. And I've seen different terminologies used, input force, output force. The one that I've seen used in your exams most often, and so that's the one I'm going to stick with, is this is force of the effort. That's what the E means. This is distance of the effort. This is force of the load. This is distance of the load. And so we put those terms into this little equation, and that gives us the law of the lever. That's what this is called. And so let's work this out using an example. So let's say this rock weighs 300 kilograms. And let's say this distance here, distance of the load, is equal to 0.2 meters. And this distance here, distance of the effort, is equal to 1 meter. And we want to know how much effort does it take to balance this system, or to get this lever to the point where, you know, you've just got the rock and the dude pushing down, and you've got those things perfectly balanced. So you could really move the lever to lift the rock by putting in a little bit more force, or drop the rock by taking a little bit of force away. So before we do that, well, we measure force in newtons. So 300 kilograms is not going to cut it. We need our force. So force equals mass times acceleration. We know that our mass is 300 kilos. We use the shorthand of 10 meters per second for our acceleration number. And so that gives us 3,000 newtons. All right. Now, what we need is, we know force of the load, right? We know that's 3,000 newtons. We know distance of the load. We know distance of the effort. So we know this and this and this. The one thing we don't know is force of the effort. So we need to get that term on its own. And the way that we do that is we just divide both sides by, well, in this case, we want to get force of the effort on its own. So we're going to divide both sides by distance of the effort. We can cancel out these terms, and then we can rewrite our equation as force of the effort is equal to force of the load multiplied by distance of the load over distance of the effort. And if we put in our terms, our load force is 3,000 newtons. Our load distance is 0.2 meters. And our distance of the effort is 1 meter. And so what we find out is that an input force, or an effort force, of 600 newtons balances this lever. So in this situation, you put in, 600 newtons, which is, not a huge amount of force. Most people could manage that. You're just putting your body weight into that to balance a 300 kilogram or a 3,000 newton load of a big old rock, which is, kind of interesting when you think about it. it's an amazing force multiplier. So speaking of force multipliers, this is going to bring us to this thing called mechanical advantage. Mechanical advantage, which we abbreviate as MA. Now, to find the mechanical advantage, we take our load and we divide it by our effort. And so if we did that for this example, 3,000 newtons divided by 600 newtons, that's going to give us 5. And what we do is we express mechanical advantage as a ratio. So that's 5 to 1. And what that's telling you is that for each unit of effort that you put in, you get 5 units out as your load. So you get 5 times more force than you put in. Now, you can also do these sort of problems really, really quickly, because for leverage problems, instead of just taking, figuring it out and then going, okay, well, now I need to find my mechanical advantage by, I know my load and I know my effort and I can use it like this. If we look at the ratio between the distance of the effort and the distance of the load, well, that gives us the same figure as knowing the load and the effort. So if we go for a lever, MA equals distance of the effort divided by distance of the load, and this is 1 and this is 0.2, then what we come up with is 5, and we express that as a ratio, and that's 5 to 1. And so being asked this question, I could also solve it by writing down MA equals distance of the effort over distance of the load. I know my distance of the effort is a meter. I know my distance of the load is 0.2 meters. That's giving me a mechanical advantage of 5 to 1. And so we go load equals 3,000 newtons. We'd still have to figure that out. And now we need to go, okay, so my mechanical advantage is 5 to 1. So I'm putting in 5 times less effort to balance that. And so all I got to do is divide that by 5. And that's going to give me 600 newtons effort. And that's a much, much quicker way of figuring that out. So that can be super handy. Now, you've got a couple of different kinds of levers. You've got a first-class lever. Now, a first-class lever is one that's like a seesaw. And the way that I remember it is to go, okay, first-class lever is this one. If my fulcrum's in the middle and my effort and the load are on either side, that's a first-class lever. If my fulcrum is up the end and then my load is closer to the fulcrum and my effort is further away, that's a second-class lever, right? This wheelbarrow, here's the fulcrum, here's the load, here's the effort. That's a second-class lever. And a third-class lever, if you've got a fulcrum and an effort and then a load, and the effort is closer to the fulcrum, that's a third-class lever. Now, the second-class lever can only ever give you a mechanical advantage because the load will always, or the distance of the load will always be shorter than the distance of the effort. A first-class lever can give you a mechanical advantage, or it can give you a mechanical disadvantage. If you put your effort over here so that your distance effort is shorter than your distance load, well, that's going to give you a mechanical disadvantage, right? It's actually going to be harder to lift your load. You're going to have to put in more force than the load. And a third-class lever, that's only ever going to give you a mechanical disadvantage because your effort or distance effort is always going to be shorter than your distance load. Otherwise, the problems work exactly the same. So what you need to do when you look at a lever problem is you need to figure out, okay, where's my distance effort? Where's my distance load? And am I having to figure out the force of the effort or the force of the load? Because there'll be one unknown term. And that's levers. Oh, before we go, I should say, there's a thing called a velocity ratio, right? Let's consider our boulder example again, real quick. So, if we look at the distance that this effort needs to move to move the load a very small distance, right, the effort needs to move much, much farther, right? So think about it this way. If you're gaining force, right, if you're gaining, if you've got a mechanical advantage, then you are going to be losing distance and you're going to be losing speed. So distance and speed is velocity. So we say that it has, that's what we say. We say we have a velocity ratio, and in a scenario where we're gaining mechanical advantage, we are losing velocity. Like this, our load is going to move much slower than our effort. It's also going to move much less far. We will look at that in some more detail when we do some sort of more complicated questions around linkages and things like that. But I think as torque and levers, this will do quite nicely. All right, cheers.